Hello and welcome to NEET Prep Go. So today we'll be doing the chapter S Block element from class 11th NCERT line by line. So let's get started without further ado. The first element of alkali and alkaline metals differs in many respects from the other members of the group. So this is something that we will study in detail further in the chapter. That is the first element of alkali, that is group 1 elements, and alkaline earth metals, that is group 2 elements. They both differ in many respects or aspects from the other members of the group, that is the first element of theirs. So you can say that the first element of group 1 as well as group 2 elements of alkali and alkaline earth metals, they differ from the other members of their own group. So they show anomalous behavior. Okay, because they show anomalous behavior. Now let's see further. The S block elements of the periodic table are those in which the last electron enters the outermost s orbital. So we know how electronic configuration works, that is 1s2, 2s2, 2p6, 3s2. So when the last that is the last electron enters the s orbital, that is 1 or 2, then we put those elements under the group 1 and 2, that is those elements whose last electron enters into the p orbital, and they are the s block elements. So the S block elements of the periodic table are those in which the last electron enters the outermost s orbital. As the s orbital can only accommodate 2 electrons, two groups, that is to the S block of the periodic table, that is group 1 of the periodic table and group 2 of the periodic table, belong to the S block. Now group 1 of the periodic table consists of the elements lithium, sodium, potassium, rubidium, cesium and francium. So like this it will go: lithium, sodium, potassium, rubidium, cesium and francium. They are collectively known as alkali metals. So these are the group 1 elements of the periodic table, that is S block elements, and all of these are known as alkali metals. Why are they called as alkali metals? This is because they form hydroxides on reaction with water, which are strongly alkaline in nature. So since the alkali metals form hydroxides in nature with water, that is when reacted with water, because they are and they are strong, that is which are strongly alkaline in nature, that is the hydroxides on reaction with water. Therefore we can say that the group 1 elements are called as alkali metals. Then we come to group 2 elements, that is the group 2 elements. They include beryllium, magnesium, calcium, strontium, barium and radium. Beryllium, magnesium, calcium, strontium, barium and radium. So group 1 elements are lithium, sodium, potassium, rubidium, cesium and francium. And group 2 elements are beryllium, magnesium, calcium, strontium, barium and radium. Okay, so these elements, with the exception of beryllium, are commonly known as alkaline earth metals. Now beryllium, as you can notice, is the first element of the alkaline earth metals, or group 2, that is group 2 elements, and it is going to show anomalous behavior. Obviously it is going to be different than the all other elements of that group. So therefore these elements, with the exception of beryllium, are commonly known as alkaline earth metals. So the group 1 elements of the S block are known as alkali metals. Why? Because they form hydroxides on reaction with water, and these hydroxides are strongly alkaline in nature. And the group 2 elements are known as alkaline earth metals because their oxides and hydroxides are alkaline in nature, and these metal oxides are found in the Earth's crust. So why group 2 elements are known as alkaline earth metals? This is because in group 2 elements, that is the oxides as well as hydroxides of group 2 elements are alkaline in nature, and these metal oxides are found in the Earth's crust. Okay. So why alkali metals and why alkaline earth metals is important point. Now among the alkali metals, sodium, potassium are abundant, and lithium, rubidium, cesium have much lower abundances. So sodium and potassium among the alkali metals, they are abundant, whereas lithium, rubidium and cesium have much lower abundances. Francium, which comes, that is lowest in the group, it is highly radioactive, and its longest lived isotope, that is Fr223, has a half-life of only 20 minutes. You must have learned half-life in chemical kinetics. So it is it is said over here that francium is so radioactive that its longest lived isotope has a half-life of only 21 minutes. Of the alkaline earth metals, calcium and magnesium rank 5th and 6th in abundance respectively in the earth's crust. Strontium and barium have much lower abundances. Beryllium is rare, and radium is the rarest of all, comprising of only 10 to the power 10% of igneous rocks. So in alkaline earth metals, calcium and magnesium are ranked 5th and 6th in abundance, that is they are of greater abundance, calcium and magnesium. Whereas strontium and barium, they both have lower abundances as compared to calcium and magnesium. Beryllium is rare, okay, and radium is the rarest of all, even rarer than beryllium, and it only comprises of 10 to the power 10% of igneous rocks. What are igneous rocks? That is when there is a volcano, then when it cools down, that is magma, molten rock. When it cools down and it hardens, then it is called as igneous rock. So of the igneous rocks, 10 to the power 10% is radium. The general electronic configuration of S block elements is noble gas, then NS1. For alkali metals, it is noble gas NS2. For alkaline earth metals, it is NS2. So basically, let's say I have to write sodium and potassium. So we know that hydrogen, helium, lithium, beryllium, boron, hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, and this is 11, 12. So neon NS1. Similarly, here also neon NS2. Okay, so how 2s2, 2p6, 3s1. So this will be 3s1, this will be 3s2. So first you write noble gas configuration. Instead of writing the entire thing, if I say write for rubidium or cesium, then you can't sit writing the entire thing, right? So you will take the noble gas which is closest, and then you know that ultimately you are going to get either NS1 or NS2 after the noble gas. So this is the electronic configuration. For alkali metals, it is first noble gas configuration, or if there is no noble gas, that is the first element, lithium and all, then also it's, and then NS1, or if it is alkaline earth metals, then NS2. Okay, so lithium and beryllium The first elements of group 1 and group 2 respectively exhibit some properties which are different from those of the other members of the respective group. So lithium as well as beryllium, both of them in the first line also we heard, they are the first elements of group 1 alkali metals and group 2 alkaline earth metals. Why group 1 is called as alkali metals we just read, this is because they form hydroxides with when reacted with on reaction with water, and those are strongly alkaline in nature. And why group 2 are called as alkaline earth metals, this is because the group 2 elements are called as alkaline metals because their oxides and hydroxides are alkaline in nature and they are found in earth's crust. Okay, so lithium, beryllium are the first elements of group 1 and group 2 respectively, which exhibit some properties which are different from those of the other members of the respective group. So these properties are called as anomalous properties. Why? Because they are different or not normal. Like both the elements should accordingly follow should be similar to their respective groups and should be similar to the members of their group, but they are differing from the norm, you can say. So therefore they are anomalous, and these anomalous properties, they resemble, this is very important, the second element of the following group. Thus, lithium shows similarities to magnesium and beryllium shows similarities to aluminium in many of their properties. So, you can say that we have lithium, sodium, magnesium. So, lithium of group 1, it resembles the properties to magnesium, which is of group 2, and diagonally you can see it's not in the same period, it is in the right adjacent, that is one period down and adjacent group. So lithium shows similarities to magnesium. Similarly, beryllium shows similarities to aluminium. Again, wait. And lithium to magnesium. Okay, and of the third group, beryllium shows similar properties to aluminium and many of their properties, and aluminium is in the third group. So this type of diagonal similarity, because you can see diagonally they both are similar, that is lithium of group 1 alkali metals is similar to magnesium of group 2, and beryllium of alkaline earth metals group 2 is similar to aluminium of group 3. So this diagonal similarity is commonly referred to as diagonal relationship in the periodic table. The diagonal relationship is due to similarity in ionic sizes or charge by radius ratio of the elements. Monovalent sodium and potassium ions and divalent magnesium and calcium ions are found in larger proportions in biological fluids. So in bio, you'll know that, or you'll notice that Na plus 1, then your K plus 1. These are all very important extracellular, intracellular fluids. That is, they help in exchange of that is from higher concentration to lower concentration. We have the sodium potassium pump also, NaK plus pump. So it is very important in biological fluids. Similarly, Mg plus 2 magnesium as well as Ca, both calcium also, both of them, they are found in large proportions in biological fluids. These ions perform important biological functions such as maintenance of ion balance, right? Ion balance and nerve impulse conduction. So you'll know that in a neuron, that is when that is when the neurons get excited, that is the membrane, because of sodium and potassium only the excitation and that is depolarization and polarization of the membrane occurs. So therefore Na plus 1 and K plus 1 monovalent ions, and sodium and potassium ions, and Mg+2 and Ca+2, that is divalent magnesium and calcium ions, are very important and biological fluids, that is important biological functions such as maintenance of ion balance and nerve impulse conduction takes place by them. Okay, so now we come to officially group 1 elements, that is alkali metals. The alkali metals show regular trends in their physical and chemical properties with the increasing atomic number. The atomic, physical, chemical properties of alkali metals are discussed below. So as we go down the group, the one extra shell gets added, so that is the radius keeps increasing. Okay. So here it is written that alkali metals show regular trends in the physical and chemical properties with the increasing of atomic number. As the atomic number increases, okay, down the group, all those physical and chemical properties such as atomic size, then your radius, metallic character, and everything, all those properties that were there in periodic classification, that is periodic properties and classification periodic table chapter, all those properties, regular trends can be seen. Now electronic configuration we have already seen, that is all alkali metals have one valence electron, okay, in group 1. So because S block element means the last electron will enter the s orbital, and we know s orbital is going to have either 1 or 2 electrons, so therefore there are two groups. If there is one valence electron, then group 1, if two valence electron, then group 2. So, and group 1 we know is alkali metals because they on reaction with water they form hydroxides which are strongly alkaline, and we know that group 2 because and group 2 are called as alkaline earth metals because their oxides as well as hydroxides are alkaline in nature as well as found in the earth's crust. So now we come to group 1 alkali metals which have one valence electron outside the noble gas core. So the loosely held s electron in the outermost valence shell of these elements makes them the most electropositive metals. This is very important. So the loosely held s electron in the outermost valence shell of the that is of the alkali metals or group 1 elements, it makes them the most electropositive metals. They readily lose the electron to give monovalent M plus ions, hence they are never found in the free state in nature. So basically, since they have only one valence electron, if they give it away, then they will attain noble gas configuration. So therefore, they are the most electropositive element because they have this one valence electron which is loosely held, and that is they lose it readily, okay, to give monovalent M plus ions. Therefore, you will notice that S block elements are never found in free state in the nature. That is, the loosely held s electron in the outermost valence shell of these elements makes them the most electropositive metals, and therefore they readily lose electron to give monovalent M plus ions, and they are never found in free state in nature. Now let's see, lithium 1s2 2s1, sodium 1s2 2s2 2p6, this is the neon configuration, then 3s1. Similarly 1s2 2s2 2p6, 3s2 3p6, this is argon configuration, then 4s1. Similarly rubidium 5s1, cesium 6s1, francium 7s1. Okay, so you can see that all the last that is the valence electron is always in the s orbital, and only one electron is there. So, and you can notice that it loses, if these elements lose this one valence electron which is loosely held in the s orbital, then they will attain noble gas configuration. So therefore they readily use it, and their that's why their electron, that is ionization energy, is lesser as compared to if you see group 17 elements. So according to that, because they readily lose the electron, right? Atomic and ionic radii. So the alkali metal atoms have the largest sizes in a particular period. How? So we know that when we go down the group, then one shells keep getting added, so the radius increases. Therefore down the group तो atomic radii बढ़ेगा. But while going across in a period, one electron keeps getting added. So basically the nuclear charge increases and the size decreases. So basically across a period, the highest, that is the largest atomic radii, that is largest size across a period, is going to be of the first, that is the alkali metal. They have the largest size in a particular period of the periodic table. With the increase in atomic number, the atom becomes larger. The monovalent M plus are smaller than the parent atom. The atomic and ionic radii of alkali metals increase on, obviously. So that is when M gave one electron away and changed to M plus, then it is going to be, the atomic size of M plus is going to be lesser than the neutral. And hypothetically, like if we take an element A, then A plus is going to be lesser than A neutral, which is going to be lesser than A with a negative charge. So the monovalent ions M plus are smaller than the parent atom, and the atomic and ionic radii of alkali metals increases on moving down the group. That is, they increase in size while going from lithium to cesium, because how one new shells keep adding up. Ionization enthalpy. The ionization of alkali enthalpy of alkali metals is considerably low and decrease down the group from lithium to cesium. Yeah. So like I said, if you have one electron, then, and you know that if you lose this one electron, then you will gain a noble gas configuration. तो इतना energy क्यों डालना है इसको ये करने के लिए? See, more energy, that is more ionization enthalpy, is required when, let's say, I have chlorine और ब्रोमीन, that is एक इलेक्ट्रॉन से मेरा नोबल गैस कन्फिगरेशन हो जाएगा, तो इसीलिए एक इलेक्ट्रॉन और you can say that is a noble gas also, it has highest ionization enthalpy because it is stable, right? So एक इलेक्ट्रॉन निकालना from something, an element which is stable, it will take a lot of energy. But in this case, ionization enthalpy of alkali metals is considerably low and it decreases down the group from lithium to cesium. Okay, because एक इलेक्ट्रॉन निकालने में when it is going to attain noble gas configuration, so इतनी ज़्यादा energy नहीं लगेगी. This is because the effect of increasing size outweighs the increasing nuclear charge, and the outermost electron is very well screened from the nuclear charge. So the ionization enthalpy of alkali metals is considerably low. We know why. Okay, and it decreases down the group from lithium to cesium. So the ionization enthalpy decreases down the group from lithium to cesium. This is because the effect of increasing size outweighs the increasing nuclear charge. Since the size keeps increasing, it outweighs the increasing nuclear charge, and the outermost electron is very well screened from the nuclear charge. The outermost electron is screened from the nuclear charge, so therefore the attraction is very less. So since the attraction is very less, so now first reason is, so firstly, that is, it has only one electron, so therefore it will give the one electron and it will attain a noble gas configuration. Therefore the ionization enthalpy of alkali metals is considerably low. Why does the ionization enthalpy decrease down the group from lithium to cesium? This is because since the size keeps increasing from lithium to cesium, it outweighs the increasing nuclear charge. So as the size keeps increasing, the nuclear charge, that is with the outer external most electron, that is if 2-3 shells come in between, then screening effect is done, that is by the shells which come in between. Let's say this is your 5s1 or 6s1 electron, and from the nucleus that is in between there are shells, due to which screening effect takes place, that is the charge gets screened. Therefore the nuclear charge, even though it increases down the group, the size as compared to the increasing of nuclear charge is more, that is increases more. So hence force of attraction decreases and it is very easy to remove the outermost electron. So as we go down the group, as the shells increase, as the atomic radius gets higher, the nuclear charge gets screened by the shells coming in the middle, and the that is the outermost electron or the valence electron, which is in the s orbital. It can easily or readily get loose without giving much energy, and in fact giving lesser energy than its previous group member, that is on top. So from lithium to cesium, the ionization enthalpy decreases. Now we come to hydration enthalpy. Hydration enthalpy of alkali metals decreases with increase in ionic size. So as the ionic size increases, the hydration enthalpy decreases. Lithium has maximum degree of hydration, and for this reason lithium salts are mostly hydrated. So as the size will increase, it will become difficult for it to uh, combine with water and readily move. So you have to remember that the hydration enthalpy of alkali metals decreases with the increase in ionic size. So as the ionic size increases, the hydration enthalpy decreases. So from lithium to cesium, lithium is going to have highest hydration enthalpy and cesium is going to have lowest. Lithium has maximum degree of hydration, and for this reason lithium salts are mostly hydrated. LiCl.2H2O. Now, all the alkali metals are silvery white, soft and light metals. Why? Because of the large size, these elements have low density, which increases down the group from lithium to cesium. So, because of the large size, the elements have low density, which increases down the group from lithium to cesium. However, potassium is lighter than sodium, so this is an exception. So the density, that is, increases from lithium to cesium, but potassium is lighter than sodium, so this is an exception. The melting and boiling point of the alkali metals are low, indicating weak metallic bonding due to the presence of only a single valence electron in them. So the melting and boiling points of alkali metals are low, indicating a weak metallic bonding due to the presence of only a single valence electron. So since they only have a single valence electron, the metallic bonding is weak, and therefore the melting and boiling points are very low for alkali metals. The alkali metals and their salts impart characteristic color to an oxidizing flame. This is because the heat from the flame excites the outermost orbital electron to a higher energy level. When the excited electron comes back to the ground state, there is emission of radiation in the visible region as given below. So the melting and boiling points of the alkali metals are low, indicating that there is weak metallic bonding due to the presence of only a single valence electron in them. The alkali metals and their salts impart characteristic color to an oxidizing flame. This is because the heat from the flame excites the outermost orbital electron to a higher energy level. When the excited electron comes back to the ground state, then there is emission of radiation in the visible region. Alright, so we saw that all the alkali metals are silvery white, soft and light metals because because of the large size that is because of the large size, they all have low density, which increases down the group. That is, the density increases from lithium to cesium. So cesium will have highest density, lithium will have lowest, but the exception is potassium, which is lighter than sodium. So the density of potassium is going to be lesser than sodium. The melting and boiling points of the alkali metals are low, so they can easily melt or easily like the boiling points and melting points both are very low because there is weak metallic bonding. Why? Because there is only a single valence electron in them. The alkali metals and their salt impart characteristic color to an oxidizing flame. This is because the heat from the flame excites the outermost orbital electron to a higher energy level. So the alkali metals and their salts impart characteristic color to an oxidizing flame. This is because the heat from the flame excites the outermost orbital electron, that is a single valence electron, to a higher energy level, and when the excited electron comes back to the ground state, then there is emission of radiation in the visible region. Therefore, lithium oxidizing flame, that is lithium gives crimson red color, sodium gives yellow, violet, potassium gives violet, rubidium gives red violet, and cesium gives blue colored flame. So this need to be remembered, that is the alkali metals and their salts give characteristic color to an oxidizing flame. That is because the heat from the flame excites the outermost orbital electron to a higher energy level, and when it comes back to the lower energy level, we know that coming back from higher to lower, emission takes place, lower to higher, absorption takes place. So when it comes back, then emission of radiation takes place, and this is in the visible region. So since it is in the visible region, that is lithium gives crimson red, potassium yellow, sodium yellow, potassium violet, rubidium red violet, and cesium gives blue colored oxidizing flame. So lithium gives crimson red, um, cesium gives blue, rubidium gives red violet, sorry, rubidium gives red violet, potassium gives violet, and sodium yellow. Alkali metals can therefore be detected by the respective flame test and can be determined by flame photometry or atomic absorption spectroscopy. So alkali metals can be detected by their respective flame test. How can you detect alkali metals? By the respective flame test and can be determined by flame photometry and atomic absorption spectroscopy. These elements, when irradiated with light energy absorbed may be sufficient to make the atom lose electrons. So when these elements are irradiated with light, then the light energy absorbed is going to be sufficient to make an atom lose electron, since it has only one loosely bounded electron to it. So now let's see. Atomic number of lithium is 3, sodium is 11. Just read through this. Atomic number of potassium is 19, rubidium 37, cesium 55, and francium 87. Atomic mass for lithium is approx 7. For sodium is 23. We take it as 23. Potassium is approx, you can take 39. Then rubidium 85, cesium 133 you can take, and francium 223. Electronic configuration, that is noble gas helium, then 2s1, neon 3s1, argon 4s1, krypton 5s1, xenon 6s1. Then ionization enthalpy is 520, that is kilojoule per mole for lithium, 496 for sodium, 419 for potassium. So you can see that you can see the trends now. You can see that the ionization enthalpy slowly decreases down the group. Why? Because the shells are increasing, and as the shells are increasing, the nuclear charge, even though it increases, still with respect to the increasing of the shells, that is, if this is the single valence electron, then even with each and every addition of the shell, that is, screening effect takes place, and it can more easily uh, be lost, or it can give up more easily, lose electron more easily. So ionization enthalpy is 520 kilojoule per mole for lithium, 496 for sodium, 419 for potassium, 403 for rubidium, 376 for cesium, and approx 375 for francium. Okay, so 520, 496, 419, 403, 376, and 375. You don't have to remember the values as per se, but you should remember uh, how ionization enthalpy decreases down the group and why it decreases down the group. Hydration enthalpy also decreases down the group because we saw that as the ionic size increased, the hydration enthalpy decreased. So 50 minus 506, 406, 330, 310, 276. Yeah. Then metallic radius. Then metallic radius. So metallic radius we can see increases down the group because of the addition of the cells. So it is in picometers. So 152 for lithium, then 186 for sodium, 227 for potassium, 248 for rubidium, 265 for cesium. Ionic radius also increases down the group. Metallic radius, ionic radius 76, 102, 138, 152, 167. Then melting point, boiling point. So melting point reduces down the group. Boiling point also reduces down the group. Melting point and boiling point are generally also very low because there is only a single electron and very loosely bounded and many shells. So therefore, more and more easily as the atomic radius increases, nuclear charge will decrease. So therefore, it will be even at a lesser temperature, that is, it will be able to melt or boil. Now density, that is density with the exception of sodium and potassium, we can see that that is the density increases from lithium to cesium. So down the group, the trend is of density is that down the group it increases. Okay, it increases, but the exception is sodium and potassium, in which sodium has a higher density than potassium. So this is an exception. Standard potentials. So, and occurrence in atmosphere. It is in parts per million. Percentage by weight. So this property makes cesium and potassium, where were we? Alkali metals can be detected by their respective flame test. So we know that lithium's flame test gives crimson red, sodium gives yellow, potassium gives violet, rubidium gives red violet, and cesium gives blue color. So alkali metals can be detected by their respective flame test and can also be determined by flame photometry or atomic absorption spectroscopy. These elements, when irradiated with light, the light energy absorbed may be sufficient for to make an electron lose to make the element lose electron, and this property makes cesium and potassium useful as electrodes in photoelectric cells. That is because when irradiated with light, the light energy which is absorbed is enough to make them lose electron. So cesium and potassium, in cesium and potassium, it is useful as electrodes in photoelectric cells. This is an important point. Now chemical properties. We are done with the physical properties. Now we come to the chemical properties. The alkali metals are highly reactive due to their large size and low ionization enthalpy. Okay, since they have low ionization enthalpy with very less energy, they readily lose their single valence electron, and they have very large size. So the nuclear charge is also not that much to the loosely bound electron in the s orbital. Therefore, they are highly reactive. The reactivity of these metals increases down the group. So the reactivity of these metals increases down the group. Reactivity towards air. The alkali metals tarnish in dry air due to the formation of their oxides, which in turn react with moisture to form hydroxides. So in dry air they get tarnished, in a way like you can say kind of rusted. Not exactly rust because it is used for iron Fe. But similarly, Similar to that, they get tarnished in dry air due to the formation of their oxides, which in turn react with moisture to form hydroxides. Why? Because they are very reactive. Since alkali metals are so reactive, they tarnish in dry air. That is, they start reacting with dry air and they form oxides. And later, the oxides react with moisture and form hydroxide. They burn vigorously in oxygen forming oxides. Because they are so reactive, they burn vigorously in oxygen forming oxides. Lithium forms monooxide, sodium forms peroxide, and the rest all other metals form superoxide. So this is also very important. The superoxide O2 minus ion is stable only in the presence of large cations such as potassium, rubidium, and cesium. So firstly, lithium forms oxide, okay, Li2O. Sodium forms peroxide, Na2O2. You know, peroxide like H2O2. Similar to that, Na2O2. Then rest all, that is rubidium, potassium, that is potassium, rubidium, cesium, they all form superoxides, MO2. Okay, so this is very important. That is, lithium forms oxide, sodium forms peroxide, and potassium, rubidium, and cesium form superoxide. In all these oxides, the oxidation state of the alkali metal is +1. So in all of these oxides, the oxidation state of alkali metal is +1. Lithium shows exceptional behavior in reacting directly with nitrogen of air to form nitride. Li3N as well, because of their high reactivity towards air and water, alkali metals are normally kept in kerosene oil. So in all these oxides, the oxidation state of the alkali metal is going to be +1. So Na's oxidation state is going to be +1. Potassium, rubidium, cesium, and superoxide is also going to be +1. Lithium is also going to be +1 oxidation state. Lithium shows exceptional behavior in reacting directly with nitrogen of air to form nitride. So lithium, this is also very important, lithium shows exceptional behavior in reacting directly with nitrogen present in air to form nitride, Li3N as well. Because of their high reactivity towards air and water, alkali metals are normally kept in kerosene. So because that is, in air the reactivity is so high, so that it forms oxides, then it readily forms hydroxides, then that is monooxide for lithium, peroxide for sodium, and superoxide for potassium, rubidium, and cesium. Therefore they are stored in kerosene oil. What is the oxidation state of K in KO2? That is, we just read, that is whether it be oxide, whether it be peroxide, whether it be superoxide, that is the oxidation state of alkali metals is going to be +1. Now we come to reactivity towards water. Give me just a minute. So the alkali metals react with water to form hydroxide and dihydrogen. The alkali metals react with water to form hydroxide and dihydrogen. 2m plus 2H2O gives 2m plus 2OH minus plus H2. Considering that M is an alkali metal, so the alkali metal M reacts with water to form hydroxide and dihydrogen. It may be noted that although lithium has the most negative electron gain enthalpy, its reaction with water is less vigorous than that of sodium, which has less negative E0 value. among the alkali metals. This behavior of lithium is attributed to its small size and very high hydration energy. Other metals of the group react explosively with water. They also react with proton donors such as alcohol, gaseous ammonia, and alkynes. The alkali metals react with water to form hydroxide and dihydrogen. That is, an alkali metal M reacting with H2O will form hydroxide 2H minus plus dihydrogen H2. It may be noted that even though lithium has the most negative electron here enthalpy value, its reaction with water is less vigorous than that of sodium. Sodium has least E negative value. Still, the reaction of lithium with water is less vigorous than that of sodium. This behavior of lithium is attributed to its small size and very high hydration energy. Since hydration energy decreases down the group, because lithium has the smallest size as well as very high hydration energy, its reaction with water is less vigorous than that of sodium. Other metals of the group react explosively with water, but lithium doesn't. They also react with proton donors such as alcohol, gaseous ammonia, and alkynes. Alcohol, gaseous ammonia, and alkynes. Reactivity towards dihydrogen. The alkali metals react with dihydrogen at about 673 Kelvin and lithium at 1073 Kelvin to form hydrides. All the alkali metal hydrides are ionic solids with high melting points. All the alkali metal hydrides are ionic solids with high melting point. 2m plus H2 gives 2m plus H minus. Then reactivity towards halogens. The alkali metals readily react vigorously with halogens to form ionic halides, M plus X minus. However, lithium halides are somewhat covalent. This is because of the high polarization capability of lithium ion. The distortion of electron cloud of the anion by the cation is called as polarization.
এটা দিবি না